Okay, so let's have a look at some integration by inspection. It's also called the guess and check method. This is particularly recommended if you're doing a course like the IB standard level, that's the 2020 exam, or the IB standard level analysis, the 2021 exam. That's because for this course, you can always do integration by inspection. You're never going to have to use substitution. And whilst you can use substitution, personally, I would recommend inspection. I think it's got a higher probability of success. So I'm going to have a look at how to do that. There's basically a couple of rules to learn, and once we use those rules, then hopefully things become clearer. Here's the first one. If we're integrating something with a function on the bottom, and then the differential of the function on the top, we're going to guess that the integral is going to be something like ln of a function that was on the bottom. So f dash x over f of x, we're going to guess something to do with ln f of x. And just run through a couple of quick examples, and then before we have a look at some past paper questions. Here's the first one. We've got 3x squared on the top, we've got x cubed plus 1 on the bottom. We notice that the bottom x cubed plus 1 will differentiate to 3x squared. Therefore, we guess it's going to be ln x cubed plus 1 plus c, and it is. And equally, let's have a look at this one here. We've got ex plus 1 on the bottom, ex on the top. Ex plus 1 differentiates to e to the x. So again, we guess it's ln of ex plus 1, and again, it is. If you're kind of wondering what's happening, it's because of the chain rule. If we try to differentiate this function, we get back to this. Therefore, if we integrate this function, we must be getting this function here. Okay, you probably need to be quite confident with the chain rule for this to make sense. Okay, so that's a couple of them. Let's have a look at some more. Same idea really. We've got x cubed plus x on the bottom, 3x squared plus 1 on the top. Yeah, what x cubed plus x will differentiate to what's on the top. Therefore, I guess ln x cubed plus x. Same again for this one. X4 plus 1 differentiates to 4x cubed. I get this. This one's, I think, is very slightly different. I've got an x4 plus 1 on the bottom. If I differentiate that, I'm going to get 4x cubed. Well, I look at the top and actually I've got an 8x cubed. Well, I've got a 4x cubed, I need to get an 8x cubed, therefore I just stick a 2 on the front. So rather than ln x4 plus 1, I just stick in 2 ln x4 plus 1. And then same again on this one. If I differentiate the bottom, I get 4x cubed. I look at the top, actually I've only got 2x cubed on the top, therefore stick a half on the front. So it's going to be a half ln x4 plus 1. And then 2 or 3 quick ones to finish off. This one we've got a sine and a cos. Cos differentiates to minus sine. Same again, it's going to be ln cos x plus c. This one's worth just mentioning, tan x, because tan x is the same as sine over cos. So you'll notice it's almost exactly the same as the one above. The only difference is that when I differentiate cos x, I'm going to get minus sine x. Therefore, I need to stick a negative on the front. So tan x will actually integrate to minus ln of cos x plus c. And then the last one, here we go, e 2x plus 1. If I differentiate it, I'm going to get 2e to the 2x using the chain rule. I need to get 4e to the 2x, stick a 2 on, and just to be accurate, let's stick a plus c on there as well. Okay, so that's that first rule. Now, the other rule, and this kind of may look super complicated, but I think once you've got your head around it, it's not as terrible as it looks. There are other things that can happen. The first one is where we have a function to a power and then times by the differential of that function. Okay, so let's just have a look at that. Say here we go, I've got an x cubed plus x to the power 5, so there's a function to a power and it's times by the differential of that function. So x cubed plus x will differentiate to 3x squared plus 1. Okay, so in this situation, this is my rule. My rule is that I'm going to guess. I'm just going to ignore the f dash x bit. I'm just going to look at the f of x. I'm going to increase the power by 1, and I'm going to divide by the new power. So let's have a look at this from the example. For x cubed plus x to the power 5, I ignore the differential bit. I'm going to guess it's just x cubed plus x to the power 6, divide by 6. Okay, we'll look at some more examples. So that's your first guess method for this sort of function. For the second sort of function, where we've got e to the f of x times by f dash x, we just guess e to the f of x. So in this case here, I've got 3x squared e to the x cubed, and if I want to integrate that, so let's put an integral sign there. So if I'm integrating this, well, again, I just guess e to the x cubed. So there we go, I've got the differential and then this function here. I just guess e of the function. And the last one is again very similar to the previous one. If you've got, say, cos or sine of a function times by the differential, you just do what you'd normally do with cos. So cos would go to sine, and then that's what I guess. I just guess sine of that function. So if I have 2x cos x squared, my guess is just going to be sine x squared. Okay, because cos integrates to sine, and again I just guess that that's going to be my answer. So the guess and check method is we start with this guess. We may be out by a factor of a number, but then we can work that out later. But this gets us close to, or it gets us the exact answer. So again, let's just have a look at a couple of those in practice. Here we go. So I've got 5x4 e to the x5. Well, I've got x5 there. That's the function that's going to differentiate to 5x4. So that fulfills the one with e to the x. So I'm just guessing it's going to be e to the x5. Okay, and then if you differentiate that, you will get 5x4 e to the x5, which is correct. The second one, let's have a look. We've got x4 e x5. Again, I start off by just guessing e x5, but then I need to, if you differentiate e x5, you're going to end up with a 5e x5. So therefore I need to put a 1 over 5 there, so that when this function is differentiated, I get back to this function. So that's the only thing. You just need to control the term you're multiplying by here. Let's have a look at another one. We've got an x squared plus 3 to the power 4, and then we've got 2x on the side. So again, we've got something inside here which differentiates to the thing outside. So again, my guess is just x squared plus 3 to the power 5, and then I'm guessing it's divided by 5. Okay, again, just follow my rule. Again, if I differentiate this one, yep, I do get back to this one. And then the last one is almost the same as the previous one. Again, I start with the x squared plus 3 to the power 5, and I guess it's 1 over 5. But this time, when I'm differentiating, I need to change this so it's 1 over 10, so that when I differentiate this function, I get back to this function here. So you've got to be kind of confident with using the chain rule to work out the last step. And let's have a look at 2 or 3 more, 4 more, and then actually have a look at some past paper questions in a sec. Here's another one. We've got x cos x squared. We notice we've got a function and its differential. So my guess is going to be sine x squared. I then see what happens when I differentiate sine x squared. I realize that I need to stick a half on the front, so that when I differentiate this function, I get back to this function. Same idea with this one. I've got sine ex plus 1. I guess it's going to be something to do with minus cos ex plus 1. And when I differentiate that, yep, I get back to this one. Same again for this one. And there's another way we could change this into double angles, but we can do this method. Cos x sin x, think of it like cos x to the power 1 times sin x. So if I'm using my rule, I increase the power by 1, divide by the new power. And then if you see this one here, when I differentiate this, I'm actually going to bring the power down, reduce the power by 1. And I need to stick a negative on there, because when cos x differentiates, you get negative sin x. So therefore, if I stick this on, then when I differentiate that, I get back to cos x sin x. And then last one, they've actually asked this one in an exam before, cos squared x sin x. Remember, cos x squared, it's the same as cos x with a bracket around, and then squared. So I've got a function for a power, and then times by the differential. So again, this is my guess. I increase the power of cos x by 1, divide by the new power, and again, see what happens when I differentiate, bring the power down, reduce the power by 1, times by the differential, which is going to be negative sign, therefore I stick in the negative there. Okay, and then if you're still with me, I know this is kind of tough, certainly at standard level, they can be particularly nasty on this one. So let's have a look at this one. We've got 2x on the top, and we've got a root x squared plus 3 on the bottom. like you might be tempted at first to go, well, hang on a minute, we can use our rule here. We've got f-x over fx. This rule only works when there's no powers on the bottom, so no roots, no powers of, like to the power 2 in brackets or power 3 in bracket. So we can't use that rule. But the rule we can use is to say, well, actually 2x over root of this is exactly the same as that. 2x times x squared plus 3 to the power negative a half. Now we've written it like that, we can use the rule we've just been looking at, where we just go, right, there we go, x squared plus 3 differentiates to 2x. Let's increase the power by 1, and then divide by the new power, and then we're going to see what happens. And in this case here, we get this. So basically, if we reduce the power by 1, bring this down here, and then this becomes a negative, times by 2x, yeah, then we will get back to this stage here. Okay, so we're using this rule rather than the quotient version. Again, the last one, same sort of idea. We've got 2x on the top, x squared plus 3 all squared on the bottom. Again, I rewrite it like this, 2x and then an x squared plus 3 to the minus 2. Again, my guess is I'm going to increase the power by 1, divide by the new power, and then again, if I differentiate this particular function, then I'm going to get back to this one. Okay, so all you need to do is work out the constant. Okay, so we finally got there. Let's actually have a look at some past paper questions. Here are the first two. We've got ex on the top, 1 plus ex on the bottom. First, I check that I've got this correct method. Yes, I've got f-x on the top, I've got fx on the bottom. So there's my guess. I guess y equals ln 1 plus e to the x plus c. And then let's actually work through this one, just check we're okay with this one. So y equals ln u equals 1 plus e to the x. If I differentiate that, I get 1 to the u. If I differentiate that, I get e to the x. And then therefore dy by dx does indeed give me e to the x on the top and 1 plus ex on the bottom. Okay, and there we go. So I've now proved that this function here must therefore integrate to this function here. Okay, that's the first one. Let's have a look at the second one. So you can see that's 3 marks. We didn't have to do too much work as long as you remembered the method. The second one, we've got integral of 2x over x squared plus 5. Exactly the same again. I've got f-x on the top, fx on the bottom. And so I go, right, same again. I'm going to guess ln of the thing on the bottom, which is ln of x squared plus 5 plus c. And then again, and this time if I differentiate this one, yeah, I actually get straight back to this. And that's it. I've done it. So I get, look at that, 4 marks just for basically knowing this rule. And that's it. Okay, so let's have a look at a couple. Obviously, they can be slightly more difficult than this. Here is the first one. I've got an x and then ex squared minus 1. Again, I've got the situation here where I've got the differential of a function here and e to the f of x here. So therefore, my guess is just going to be e to the x squared minus 1. And then I basically see what's going to happen if I do that. So e to the u, where u equals x squared minus 1. So dy by du is e to u dash is 2x. If I get this, I get dy by dx is 2x e to the x squared minus 1. So as you notice here that I'm basically off by a factor of 2. So I go, well, my guess here, I was 2 times too big. Therefore, my final answer must be a half e to the x squared minus 1. Okay, that's 4 marks. So there we go, got a few marks more on that one. Okay, the next question is this. This one's a bit more tricky. You've got 3x squared on the top, and then you've got an x cubed plus 1 to the power 5 on the bottom. See, this one's worth 6 marks. This time I've got the f-x here, and I've got the f of x to the power n. So I've got kind of one of the forms I can use. So I'm just going to guess that. Well, first off, I'm just going to rewrite it like this. So I'm going to rewrite it as 3x squared bracket x cubed plus 1 to the power minus 5. So that's my form, so that's in the correct form. So I'm going to use my little rule. I'm just going to increase this power by 1. I'm going to divide by this rule. So that's what I'm guessing. And then if I use the chain rule, I'm going to get this. I'm going to get this. And I get the answer. That's it. Done. So there's my guess. My guess must have been correct because when I differentiated it, I got back to the function that I was expecting to have. So now that I know what the function is, so I know that it's y equals minus 1 over 4 bracket x cubed plus 1 to the power minus 4 plus c. Now I use the boundary conditions. When x is 0, y is 1. Stick in your values. So x is 0, y is 1. Gives me this. I then solve it. I get c is 5 over 4. And therefore y is the whole thing plus 5 over 4. Okay, so if you actually remember the trick, actually 6 marks, you don't have to do that much work for, and the bonus is that most of the students won't get this correct. Okay, right, 2 or 3 more. Right, here we go. Here's the next one. This one's worth an incredible 8 marks. On part A, which we skipped to part B, we'd worked out the x-coordinate of P is 3. So let's have a look how to do this one. So first off, we notice we've got f-x over fx kind of question. This thing differentiates this thing. So we jump straight in and go, let's just guess that it's y equals ln bracket 6x minus x squared plus c. That's our guess straight off. And actually that's it. That gives us the differential, because when we differentiate ln, then we're going to get 1 over this thing times by the differential of this thing. Well, the differential of 6x minus x squared is 6 minus 2x. So that's it. Done. So we've done the first bit. We get to this bit, and we know that the x-coordinate of P is 3, the y-coordinate of P is ln 27. So let's do the next bit, which is, let's just show the whole thing. So the next bit, so I substitute this in. Ln 27 is ln 6, and then x is 3 plus c. This all simplifies out to give ln 9. Therefore, c is going to be ln 27 take away ln 9. Now, ln 27 take away ln 9, if you remember from logs, we can divide. So 27 over 9 gives us ln 3. And there we go, y equals ln 6x minus x squared plus ln 3. Like 8 marks. We did that in about 2 minutes. Like I said, as long as you remember that rule. Actually, the rest of the question is not that difficult. Okay, so there we go. And, okay, 2 more. I think. All right, here's the first one. So we've got x over x squared plus 1. Once again, we've got f-x over f of x. So that's the correct form as before. We go, right, let's guess it's just ln of x squared plus 1 plus c. Differentiate this. We're going to get 2x on the top, x squared plus 1 on the bottom. We notice we're 2 times too big, because we should have only had an x on the top. Therefore, our guess was 2 times too big, so our correct answer should be a half ln x squared plus 1 plus c. So we've done the first bit. And now this bit, we're actually going to integrate between an area, so therefore we don't need to worry about the plus c anymore. Therefore, between 0 and 4 of the function, well, we already know what it integrates to. It goes between 0 and 4, and then we stick in 4, we stick in 0, we get a half ln 70. So again, once we've got this integral correct, actually the rest isn't so difficult. Okay, right, and this one I think was definitely the last one. I saved this one till last. Again, it looks very tough at first glance, so let's see if we can do it. First off, we realise that we're going to integrate between a region. So let's actually find, we weren't given this point as 3, so let's just show how would we find x is 3. Basically, we want to find when y is 0. Well, when y is 0, 0 must be equal to this fraction. So 0 equal to this fraction. And then, think of it however you want, really. We can't divide by anything to ever make it 0. So therefore, the top bit must be 0. Or you can think about this being brought over the other side. 0 times something is 0. Anyway, we get 0 equals 6 minus 2x. We get x is 3. So now we know we're integrating between x is 0 and x is 3. Okay, we then notice, again, this is the nasty one. It's the one that is this form. You know, it's not the ln one, because we've got a root on the bottom. So let's rewrite it as 6 minus 2x, and then 16 plus 6x minus x squared all to the power minus a half. Now we've got the right form. So we go, right, let's guess. We're going to guess 1 over 0.5, 16 plus 6x minus x squared to 0.5. So we've increased the power by 1, and then we get that. And then actually, if you differentiate this, it gives us the answer. So if we bring the power down, reduce the power by 1, times by the differential of that, we actually get back to this. So we've got it. And then the key thing now is just to find plus c. So, well, 1 over 0.5 is 2, so let's just simplify that first. And then I'm just going to stick in my numbers. Again, I don't need to worry about c anymore because I'm integrating between two values. So when x is 0, x is 3, those are my two boundary conditions. I'm going to stick it into this. So when x is 3, I stick in 3. I'm going to get, ends up being root 25, which gives me 5. X is 0, stick it in. I end up getting 16, or root 16, which gives me 4. And then 10 take away 8 is 2. And again, I can't remember how many marks that was. That was at least 6, could have been 7, something like that. So again, quite a tough question. So there we go. That's how to use the kind of inspection method to do some integration.